Hello everyone, I'm Dan Fullerton, and in this video we're going to take a look at the 2017 AP Physics 1 free response questions. As I'm doing these today, the official scoring guides have not yet been released, so odds are pretty high I probably miss a couple points somewhere as we go through this. Also note it's a timed exam, which means as you're going through these, if you get stuck at some point, it's okay to move on to the next part of the question or the next question. You don't want to get bogged down if you get confused. Get every possible point on this that you can, and then when you're all done, if you have extra time, go back and work on the ones you struggled with. But let's take a look, starting with question number 1, our circuits question. They start off by giving us 3 different circuits, 1, 2, and 3, batteries hooked up to light bulbs. And the key here is recognizing that light bulbs are basically just resistors. So I would probably start out by redrawing the circuit, something like this. Circuit 1, it looks like we would have a battery connected to 1 resistor. Circuit 1, and this resistor is A. Circuit 2, pretty similar, except now we have 2 resistors in series. There's circuit 2, and these we call B and C. And finally, in circuit 3, we have our 2 light bulbs, but now they are wired in parallel. And just drawing it that way oftentimes helps me figure out what's going on. So then, part A, rank the magnitude of the potential differences across light bulbs A, B, C, D, and E from largest to smallest. And if they have the same potential difference, state that. Well, A has whatever the battery voltage is across it, and D and E, because it's in parallel, has whatever the battery voltage is across it. So I would write A equals D equals E. Those are all the same. And those are going to be greater than the voltage across B and C, because here the battery voltage is split across the 2 resistors B and C. But B and C will be equal because they say all the light bulbs are equal. So how did you determine that ranking? Well, I think I just talked through that. Now, the batteries all start with an identical amount of usable energy and are all connected to the light bulbs in the circuits at the same time. So in which circuit will the battery run out of usable energy first, and in which circuit will they run out of usable energy last? Well, that's going to be the one that uses the energy the quickest, that has the greatest power, power being the rate at which you expend energy. And the one with the greatest power is going to be 3, because we have the total battery voltage dropped across D and E, and we have 2 resistors doing that. In A, we've got the same voltage across the resistor, across the lamp, but there's only one of them. The one that's going to use the least energy, or use energy the slowest, is going to be 2. So I would say circuit 3 is most, or I guess fastest. Circuit 3 will be done first. Circuit 2 will be done last. And they want a paragraph length response that can contain equations and drawings explaining that reasoning. I'm not going to write out the paragraph. It's boring to watch me write in a video. More boring than even listening to me. Wow. But I'll talk you through what I would write. Something around the lines of power is energy per unit time. So the circuit with the greatest power dissipation will run out of usable energy first, and the circuit with the least power dissipation will run out of usable energy last. Circuit 3 uses the most power, 2v squared over r, so it will run out of energy first, and circuit 2 uses the least power, and when you calculate the power for circuit 2, that's going to be half v squared over r, so it'll run out of energy last. And you might even show your calculations for the power dissipation in each circuit. You could use a VERP table if you wanted, or just show the quick equation. Power dissipated in circuit 1 is just going to be v squared over r. Power dissipated in circuit 2 is going to be 0.5 v squared over r, and power dissipated in circuit 3 is going to be 2 v squared over r when you work all those out. And for 7 points, I think that's plenty. I'd stop there and move right on to the next question, number 2. So let's take a quick break, get set up for number 2, and on we go. All right, and we're back with question number 2, a 12-pointer, suggested time 25 minutes, so a little bit more in-depth question. And this is awfully similar to a lab you've probably done in class. It says a student wants to determine the coefficient of static friction between a long flat wood board and a small wood block. A. Describe an experiment for determining the coefficient of static friction between the board and the block. Assume equipment found in a school physics lab. We're going to draw a diagram, describe the procedure, and then derive an equation for the coefficient of static friction in terms of the quantities measured from part A. So to start this, there are a couple ways you could do this, and I actually do this two different ways in my classroom. One is you can take a flat board, put the object on it, and tilt the board up until you get to the point where it just begins to slide. If you measure that angle then, the tangent of that angle works out to be the coefficient of static friction. And you can work all through that and do the derivations and things like that. But because it's going to give us a bunch of data for different points and different things like that, and also ask us about reducing experimental uncertainty, the second way might be a little bit simpler as far as explaining and pulling that into the problem. And that is to take a block, put it on a wood board, and attach a spring scale to it. And then you pull it with increasing amount of force until it just begins to move. And if you record that force at the instant before it begins to move, that's the applied force on it. That has to exactly balance the force of static friction on it. Mu times the normal force. You can figure out mu times the normal force, so you can then calculate mu, the coefficient of static friction. So I'd probably start off with the diagram where we're going to show something like a board. We can label it board. Very exciting there. On top of it, we'll place our block. We'll attach a spring scale. Spring scale. And then we'll pull it with some applied force. On top of our block, we can place any additional masses. And what we'll do is we will record the mass of our block and the additional masses. We could do that. Additional masses. We can do that with the mass balance. It'd be an easy way to do it. With the mass balance. I'll also come over here and we will record force, the applied force, with the spring scale. All right, when you do this, if we were to make a free body diagram for our block, what we're going to have is the force of gravity, its weight down, mg, the normal force, the force of the board up on the block. We know those two must be balanced because it doesn't spontaneously accelerate up off the board or spontaneously accelerate down. We have the applied force, and we have our force of static friction. Now, if we apply Newton's second law in the x direction, the net force in the x direction is going to be the applied force minus the force of friction, and that all has to equal 0 at the point just before it begins to move, the maximum static friction force. No acceleration, so that must be equal to 0. Therefore, we could state that the applied force equals the force of static friction. We'll call that equation 1. In the y direction, we could do the same thing. Net force in the y direction equals normal force minus mg. It doesn't accelerate up or down. The acceleration must be 0, so those must be balanced. Therefore, the normal force equals mg, equation 2. Now, using the equation for friction, force of friction is the coefficient of friction times the normal force. We could solve for the coefficient of friction, which is the force of friction divided by the normal force, which, when we apply equations 1 and equation 2, we have the applied force divided by mg to give us our static friction. So that will be how we can go about deriving this. And I'd probably put this in a paragraph explanation too, something around the lines of place a wood board horizontally on a stable flat surface. The small wood block will be attached to a spring scale and pulled horizontally with an increasing force on the spring scale until it just begins to move. Record the reading on the spring scale just before the block moves, which provides a measure of the applied horizontal force on the block, the FAP, which can be shown as equal in magnitude to the maximum force of static friction on the block. You can do this multiple times, each time placing various masses on top of the wood block over here. For each trial, record the applied force and the total mass of the block with top masses at the instant the block just begins to move. Determine the coefficient of static friction as we just showed. And I think that would cover you. Now, describe the procedure to reduce experimental uncertainty. Well, the way I would go about doing that, repeat the experiment with those various additional masses. We could then plot the applied force reading from the spring scale on the y-axis versus the weight of the block and additional masses on the x-axis, and use the slope of that line to find the coefficient of static friction. Here, let's go ahead and show you, plot that out briefly. And when I did my answer, I even made a little graph to show what it would look like. We have our applied force on the y, we have our weight on the x. Wherever our points happen to be, we'll draw our best fit line. And then for our analysis here on the best fit line, if our coefficient of static friction is the applied force over mg, well, if we take a look at this in terms of y equals mx, in terms of a line, we could say the applied force is equal to mu s mg, which is equivalent to y equals mx. Over here, there's our y is FAP, which we've got there. Our x is mg, so the slope is going to give us the coefficient of static friction. So slope equals mu s. Okay, now we've actually done it. We've got some data. It says, based on the data, what conclusions should the students make about the hypothesis that the coefficients of static and kinetic friction are equal? Are they equal or not equal? Well, quite obviously, you could read that and say the static and kinetic coefficients are not equal. Although the averages appear the same, they are swayed by a single anomalous data point from lab group number 5, which has a much higher coefficient of kinetic friction and a much lower coefficient of static friction. Something went wonky with that group. This point should be noted as anomalous in the lab notebook and discounted from further calculations. So if you just look at the average, they look the same, but if you look at the data in detail, that one lab group had something funny going on. Probably worth spending some time talking to that lab group, seeing exactly what happened, maybe repeating that data point, but it obviously doesn't fit with the rest of the pattern. And finally, part D, a metal disc is glued to the top of the wood block. The mass of the system is twice the mass of the original block. What happens to the coefficient of static friction? Well, static friction, the coefficient remains the same. The coefficient of friction is a function of two things: the nature of the surfaces in contact, which haven't changed, and the normal force. Or pardon me, it's just dependent on the nature of the surfaces in contact. The force itself is determined on the normal force. Since the surfaces in contact didn't change, the coefficient of friction didn't change. The coefficient is not a function of the mass or the normal force. So part D remain the same. With that, let's move on to number 3. And we are back with number 3, our angular momentum question, another 12-point, 25-minute question, so a slightly more in-depth question. Here we have a rod of length d. It's got a pivot point, and we're going to throw a disk with some velocity v0 toward it at some distance x from the pivot. Suppose the rod is much more massive than the disk. To give the rod as much angular speed as possible, should the student make the disk hit the rod to the left of point C, at C, or to the right of point C? And from common sense, you're probably already guessing it's to the right of point C, which would be correct, but you have to explain your reasoning without manipulating equations. Really not sure why you would do this without manipulating equations. I like using equations as a guide to my thinking. But if you had to do this, I'd probably do it with the equations first and then write a couple sentences. Something along the lines of angular momentum is conserved during the collision, so you want the disk to have as much angular momentum as possible, which occurs when it is the furthest possible distance from the pivot, yet still will make contact with the rod. So correct answer to the right of point C. Next, for part B, on the internet, oh, there's some danger. A student finds the following equation for the post-collision angular speed omega of the rod in this situation, and it gives you a formula for omega. Regardless of whether that equation is correct, does it agree with the qualitative reasoning we talked about in part A? In other words, does this equation for omega have the expected dependence? And here I would say yes. And the reasoning, again, without deriving an equation, which kind of bugs me, but all right, we'll play along. I'd say something like, as x increases, angular velocity increases according to the equation. As momentum of the disk increases, which is mv naught, angular velocity increases. And as the moment of inertia, I, increases, angular velocity decreases, which are all consistent with our expected dependencies. The numerator of the equation, mxv naught, is the angular momentum of the disk, and we expect angular velocity to increase with increasing angular momentum. So all the pieces seem to be in the right place. Okay, part C. Another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with this equation for omega. Without deriving the correct equation, again, not really sure why you wouldn't actually go do that, but how can you tell that this equation is not correct? Why doesn't it make physical sense? You could do this pretty easily by saying that mass is in the denominator of this equation, which would indicate that smaller disk masses would lead to larger angular velocities, and that's just silly. Another strong indicator that something is wrong is the moment of inertia in the numerator. You would expect angular velocity to increase with smaller rotational inertias, not a direct relationship. All right, now we move on to parts D and E, a little bit more to my liking. Do not assume that the rod is much more massive than the disk. Immediately before colliding with the rod, the disk's rotational inertia about the pivot is mx squared, and its angular momentum is mv naught x. Derive an equation for the post-collision angular speed omega of the rod. Express your answer in terms of d, m disk, I, x, v naught, and physical constants as appropriate. Sorry about that. Had a little smurf over here seeing what was going on. All right, the way I would start to derive this is take a look at the angular momentum before and after the collision. Conservation of angular momentum says they have to be the same, so we could start by writing that the initial angular momentum must equal our final angular momentum, which implies then, well, if our final angular momentum is the final moment of inertia times the final angular velocity, and the initial angular momentum is mv naught x, we could then write that mv naught x is equal to our total moment of inertia times omega. Or omega equals mv naught x divided by our total moment of inertia. Now, our total moment of inertia is going to be equal to our initial I plus, we have to take into account that disk. Moment of inertia of our rod plus mass of our disk times x squared. Therefore, omega will equal mv naught x over I plus m disk x squared. And for part E, consider the collision for which your equation in part D was derived, except now suppose the disk bounces backward off the rod instead of sticking to it. Is the post-collision angular speed of the rod when the disk bounces off it greater, less, or equal to the speed when it sticks to it? Well, the answer here is going to be greater than. There is a great change in the angular momentum of the disk when it bounces backward off the rod, since angular momentum is a vector and has direction. Since it has a greater change in angular momentum, there must be a greater change in the angular momentum of the rod due to conservation of angular momentum. Since the moment of inertia of the rod remains constant, the only way you obtain a greater angular momentum in the rod is with a greater angular velocity. So I would leave greater than as your answer right there. All right, and with that, we will take a quick break. Right. And we are back with question 4. Looks like a conservation of energy sort of question, but another one where we're not really supposed to be manipulating equations. So we've got these two setups, Team 1 and Team 2, the table, slightly different heights, but the launch height of the block off of these various ramp type structures is going to be the same final height that it's going to drop as it leaves the table. So the class is asked to design a low friction slide launching a block horizontally from the top of a lab table. They assemble the slides, the identical blocks. Both slides start at the same height D above the tabletop, but Team 2 has a lower table, so they bring the right side up of their tabletop. If both blocks are released from rest at the top of their respective slides, do they land the same distance from their respective tables? The answer? No. The trick now, we have to justify our explanation. Block 1 is dropped from a higher point with respect to its launch height, so it converts more gravitational potential energy to kinetic energy than Block 2 and leaves a table with a greater horizontal velocity. Both blocks are in the air for the same amount of time since they're launched from the same height with the same initial vertical velocity of 0, but Block 1 is going to travel further since it is traveling at a higher horizontal velocity during that identical time interval. But now, in another experiment, Team 1 and 2 use tables and low friction slides with the same height. However, the two slides have those different shapes. One's a rather smooth curve, one looks a little bit more like a water slide. Both blocks are released from rest at the top of their respective slides at the same time. Which block lands further from the respective table? Well, in this case, we can say the blocks land the same distance from their respective tables. Explain again without manipulating equations? Well, both blocks have the same amount of initial gravitational potential energy because they're released from the same height, and they are launched from the table at the same height, so they leave the table with the same amount of kinetic energy and therefore the same horizontal velocity. The same amount of gravitational potential energy is converted into kinetic energy along the slide. They are also in the air for the same amount of time since they have 0 initial vertical velocity and travel the same vertical distance. Therefore, they're going to land the same distance from their tables. But, part 2, which block hits the floor first? Well, that'll be block 1. Both blocks obtain the same final speed, but they don't achieve that final speed at the same rate. Block 1 speeds up more quickly due to the steeper slope, so it reaches the edge of the table faster than Block 2, which picks up speed more slowly. Essentially, Block 1 has more time at higher speed than Block 2 because it accelerates more quickly. Therefore, Block 1 leaves the table first, and after that they have the same path. Since Block 1 leaves the table first, it's going to be the one that hits the floor first. It has a head start. And that should cover you for number 4, a nice short 7-point question. Come back in a second with number 5. Okay, and we're back to number 5, our wave question, a superposition question. Two wave pulses traveling in opposite directions on a string. The shape of the string at time t equals 0 is shown. Each pulse is moving with the speed of 1 unit per second in the direction indicated, toward each other. Between time 0 and 5 seconds, the entire left-hand pulse approaches and moves beyond point P on the string. On the coordinate axis below, plot the velocity of the piece of string located at point P as a function of time between t equals 0 and t equals 5 seconds. All right, that's kind of interesting, looking at the velocity of the string located at point P. So if we were to make a quick graph here, and we have the velocity here in centimeters per second, and over here we have our time going up to about 5 seconds. So 1, 2, 3, 4, 5. As we look at this, we kind of have to think about what's going on there at point P as those points are crossing it. Well, initially from 0 to 1 second, that pulse hasn't really gotten there, so our first part of the graph is going to look like that. Then from 1 to 3 seconds, it looks like we have a speed of about 1 centimeter per second. So we're going to see a vertical jump here to 1 centimeter per second. We'll make that 1. But from 3 to 4, where we have that steeper part as it comes and crosses part P, we're going to go down to a negative velocity. And it looks like it's steeper. I could calculate that as down here at -2. And then from 4 to, oops, I think I drew that a little bit too far. Let me redraw that over 1 second. And then from 4 to 5 there, we're back to the flat part of the graph up above. So I would think our velocity versus time graph would look something like that. And then part B, at t equals 5 seconds, the pulses completely overlap. On the grid, sketch the shape of the entire string at t equals 5 seconds. Do any scratch work on the grids on the following page. You'll only be graded for the sketch made on the grid on this page. So you're kind of doing this in the opposite direction. But here's what I would do. As you look at these, I'm just going to sketch them quickly here. At the point where they're superpositioned, draw those two. We've got one shape that looks kind of like this from the first part, and on the right hand side we have one that looks like it's coming more like that. When you add those together point by point, what you're going to see is a shape that looks kind of like this, comes down here and comes right back. So all this is superposition, adding the different values of the waves as they're overlapped to come up with the final here shown in blue. So do that neatly on the paper and I think you'd be all set. So a nice quick question if you understand what it's asking. Thanks so much for your time, everybody, and make it a great day.